Okay, so today we have kind of a mixed bag of a lesson today. We're going to talk about Millikan's oil drop experiment. We're going to talk about Rutherford's model of the atom, and we're going to talk about Bohr's model of the atom as well. A lot of these concepts are going to be old concepts, but we're going to look at this in a new way because remember, the focus is on analyzing what are the characteristics of an atom and how can we find all of the specific details about those characteristics. So here's the plan for today. We're going to discuss this the significance, it should say, of Millikan's oil drop experiment in terms of how it was used to find the elementary charge of an electron. So in other words, what is the charge of an electron? How do we figure that out? We'll also continue to a discussion on how the model of the atom developed further, thanks to Rutherford and Bohr. We're going to look at energy levels in an atom and what happens when electrons move from one energy level to another. Like I said before, it's going to be a bit of a mixed bag today, and it's probably going to be a bit of a long lesson. I apologize in advance, but let's get going. So Millikan, and again, remember, we're following the notebooklet in case you haven't already downloaded it or whatever, but Millikan, although J.J. Thomson was able to determine the charge to mass ratio of the electron, that's what we did yesterday, he could not determine either value. So he couldn't tell what the charge of an electron was or the mass. Robert Millikan, that's the guy in the bottom corner there, he was able to determine the elementary charge on an electron in his oil drop experiment. If you've forgotten what the oil drop experiment's about, I'll show you in just a second, so don't worry about that for now. But in the experiment, oil droplets were injected between two parallel plates, which were connected to a variable voltage source. When there was no charge on the plates, the droplets would fall to the lower plate due to the gravitational force, obviously. Now, however, if the plates were charged, some of the droplets would rise to the upper positive plate, which indicated some of the droplets were charged, right? And if they're rising to a positive plate, that would mean those droplets were actually negatively charged. Anyway, that picture right there kind of shows what the experiment looks like. I think that's the exact same one I showed you guys before. But Millikan was able to adjust the voltage so that some of the oil droplets became suspended. In other words, they were just floating there. When this happened, the upward electrical force and the downward gravitational force must be equal. Derive the formula that Millikan used with his oil drop experiment in order to calculate the elementary charge. Well, of course, like we said, if your force of gravity and your electric force must be equal, so if they're suspended, you have Fg equals Fe, then therefore Fg, which is mg, equals Fe, which is Eq. Or in other words, you can get Q all by itself by dividing by E on the other side. So Q is equal to mg over your electric field strength. That would tell you what the charge of one electron would be. Or at least very, well, let's be a little bit more specific here. That would tell you what the charge of the oil droplet is, right? Because if we know the mass of the oil droplet, you know the electric field strength, the charge on that would be the charge of the oil droplet. Whether it's only one elementary charge or many charges, that's yet to be determined. All right, so an oil drop of mass of that is suspended in an electric field of that. How many electrons has the oil drop lost or gained? So here's where we can actually start dealing with this. Now remember, at the time though, he had to derive what the elementary charge of an electron was in some pretty unique ways. But at least then we were able to determine from that there was always a constant value. It was always some multiple of what the constant value is. Anyway, that's not what we're going to do here. We're just going to look for how many electrons the oil drop has either lost or gained. Remember, if it lost electrons, that would mean it's positively charged. Whereas if it gained electrons, that would mean it was negatively charged. Okay, so first things first, we know our electric field is pointing up. Okay, so if we have our two parallel plates and we have an electric field pointing up, remember the electric field points where a positive charge would travel. Okay, so if a positive charge would travel this way, that would mean our top plate in this case is negative, and our bottom plate must be positive. Okay, that's going to be important because that'll help us determine whether they've lost or gained electrons. You can think about that right now. Anyway, so since it's suspended in that electric field, we can say Fg equals Fe, or in other words, mg equals Q, or E times Q. And then of course, getting Q all by itself, we can say Q is equal to mg over E. Now we know what the mass is. It gave it to us in the question itself. We know what gravity is. It's just 9.81. And we know the electric field strength because the question also gave that to us. So Q is therefore going to equal 7.2 times 10 to the negative 15 times by 9.81 divided by 1.1 times 10 to the 5. And what this gives us is about 6.42109 times 10 to the negative 19 coulombs. Now, in this experiment, of course, he was able to determine the charge of just one elementary charge. But of course, that was through many trials and tribulations, of course. But from this, we can actually tell what the number of electrons are in this, because we know what the number of electrons, or what the elementary charge is. The elementary charge is 1.60 times 10 to the negative 19. That's something that's on our formula sheet. So if we were going to look for how many electrons, we just need to divide by that, because remember, this should be more or less some multiple of this. And if you divide these two numbers together, you're going to get pretty much almost exactly equal to 4. So it's going to be 4 electrons, because 4 of these elementary charges would make this. But we need to think about whether we've lost these electrons or gained these electrons. Keep in mind, if it's suspended in a field like this, that means gravity is pushing it down, but something like an electrical force is pushing it up. Well, the only way an electrical force would be pushing it up in this case is if your object here was attracted to a negative plate, which would make that object positive. So we know our object, our oil droplet here, is positive, which means it's actually lost electrons. So we'll have to say 4 electrons lost. All right, moving on to the next one. A small plastic sphere with 10 excess electrons and a mass of that is placed between 2 horizontal parallel plates that are 5 centimeters apart. If the potential difference between the plates is 5.0 kilovolts, determine the sphere's acceleration. Assume the top plate is positive. So again, these are horizontal parallel plates. So again, we have a situation like this where we have our 2 horizontal parallel plates. It's telling us right now the top plate is positive. That makes our life a little easier. What we're looking for is the acceleration, which is going to imply that the forces are not going to be equal to each other, because again, if they were equal to each other, you'd have no acceleration, you'd have it suspended. Now, you got to think about where acceleration comes from, because we are looking for acceleration. In case you've forgotten, acceleration comes out of your net force. So we're going to have to find the net force in this case. Now, let's see here. It doesn't tell us which way it's going to go. So we can't just say which one's bigger right off the bat. So we have to just kind of go out on a limb here. I'm going to say that your net force, again, if we have our object right here, I'm going to say your net force is your force electric, because again, it has excess electrons. It's going to be your force electric minus your force of gravity. So let me just go back here, because I kind of just did like a million things in my head all at once there without explaining it. With excess electrons, we know our thing right here, our little small plastic sphere, has a negative charge. Since the top plate is positive, it's going to be attracted upwards. That'll be our Fe, and gravity, of course, always points down. So we can say our net force is Fe minus Fg. You could have gone the other way. You could have said it was Fg minus Fe. I don't know where this is going to go, but I just did that way because, again, I usually think of the upwards minus the downwards. Whatever, it really doesn't matter. Okay, let's throw things in here. F net is going to equal Fe. Fe is Eq. Fg, of course, is mg. We actually have all that information. We know, oh wait, we don't. We don't have our electric field strength. Oh, well, we don't have to worry about electric field strength because we know we have parallel plates. We know it's a uniform electric field then. So our uniform electric field is going to equal our voltage divided by our distance. That's on the formula sheet. That still can come around, so we can use that to connect back to here. So we know that our electric field strength is voltage, which is 5,000 volts, divided by distance, which is 5 centimeters, so 0.05 meters. This gives us an electric field strength of 100,000 volts per meter. There you go. Now we have everything. My mistake. So F net is going to equal 100,000 times by Q. Well, Q is 10 excess electrons. So we know it's 10 times 1 electron, which is 1.60 times 10 to the negative 19. Minus our mass. Mass was given to us 8.2 times 10 to the negative 15 times G, which of course is 9.81. Throwing this in your calculator, you're going to get F net is going to equal about 7.9558 times 10 to the negative 14, and that's a force, so it's newtons. Now what? Well, we're looking for acceleration. Remember, net force can be broken down into a mass times an acceleration, so we know this is mass times acceleration equals this number right here. I'm not going to waste my time by writing it down again. We know the mass. It's that same number from before, 8.2 times 10 to the negative 15, times by our acceleration equals, I'll be lazy again to say it's that same number up there, divided over, and you're going to find that acceleration to 2 sig digs, because that's all we got in this question, is actually it's a pretty nice number, 9.7 meters per second squared. And because that's a positive acceleration, because we also had a positive force here, because it's a positive acceleration, we know the direction on that is going to be up. Make sure you indicate a direction. It seems like it's been a long time since we've had to worry about directions. but in this case, because it's an acceleration, you do need to worry about a direction. All right, so we're moving way forward in the booklet now. Otherwise, we would have just stopped right there, and that's hardly a lesson. We're only not like 10 minutes in. So we're going to talk about Rutherford and Bohr here. But to do that, we have to, of course, talk about some of the early atomic models. We can start with Thomson's model. I know yesterday we started with Dalton's model, but Dalton's atomic model only dealt with atoms and didn't account for electrons in any way. Just thought of atoms as just being one solid cohesive piece. Both Thomson and Millikan discovered properties of negative charges. Their experiments allowed them to calculate the charge to mass ratio, that was Thomson, and the elementary charge, which was Millikan. Now, Thomson conceived a new model for the atom. To describe his model, we would just say it's an atom made of positively charged material. And then, well, that was bad, I kind of scratched it out, positively charged material with electrons embedded in them. So this is often called like the raisin bun model or the plum pudding model, right? So in other words, it's a positive base to it, and then there's a bunch of negative pieces in it. That's what J.J. Thomson thought the atom was. So he was acknowledging that the electron was a thing. Of course, he did determine the charge to mass ratio of electrons, and then that's what he came up with for an atomic model. Now, in comes Rutherford. This was in 1911. Ernest Rutherford, along with his assistant and a student, performed an experiment in which positively charged alpha particles were fired towards a very thin gold foil. Although most of the particles passed through the foil, some of the particles were deflected. So in other words, when he saw like that piece of gold foil and then those alpha particles going to it, some of them went right through, others bounced back. So what did Rutherford deduce from this experiment? Well, he deduced that the positive charge and the bulk of the mass of an atom must lie in a central mass with a radius of less than 10 to the negative 14 meters. In other words, he understood that a lot of an atom was actually just empty space, right? So in other words, he was the one who came up with that classic, like, you know, classic model where there's like a nucleus and then the electrons, ooh, there you go, electrons are buzzing around it. He was the one who came up with that. So he realized that the bulk of that mass was in that central piece, but then there was a lot of loose space all around it, right? And that's why a lot of them would just go right through that foil. Anyway, moving on. So, oh, there it is. You have to draw it. Rutherford discovered that the atom has a nucleus. He proposed the nucleus contained the positively charged protons and the negatively charged electrons were external to that nucleus, right? So he felt that in the nucleus there was positive protons and electrons were the negative piece buzzing around it. And he also felt like the scale of this was insane. He thought the nucleus was a very, very, very tiny portion of the overall scale of a full atom. Okay, anyway, moving on. So speaking of which, the radius of a nucleus of a gold atom is about that, and the atomic radius is about that. So in other words, this is just talking about the nucleus in the center, and the full-blown atom, including where like the furthest out electrons are, is this. Okay, so these are the numbers to represent a gold atom, a single gold atom. Now, if you were drawing a scale diagram of the gold atom and draw the nucleus with a diameter of 1.0 millimeters, so just a 1 millimeter nucleus, like basically like the tip of your pen would represent the nucleus, then what would the diameter of the atom be in your diagram? So before we tackle this question, think about what it's really saying. It's saying, all right, if you're going to make a scale diagram of a gold atom and you say, that right there, that dot I just drew right there, that was no accident. This dot I drew right there is your nucleus at 1 millimeter, which probably is actually, this is probably bigger than 1 millimeter on your screen right now. But if that was the nucleus at 1 millimeter, how big would the diameter of your full atom be? Let's watch this question quite carefully. This isn't really a physics question. It's more of a math question than anything. I would set this up as a ratio. And by ratio, I just mean compare equivalent proportional pieces to other equivalent proportional pieces. So here's what I would say. I would say atom 1 over nucleus 1 is going to equal atom 2, in other words, our drawing, divided by nucleus 2. In other words, the nucleus drawing, right? So for atom 1, you got to watch here that they gave us the radius of these, and we're looking for a diameter. It actually doesn't matter because it's all going to scale appropriately. So I'm not going to change these numbers, but if you were to change these numbers, remember, since we're looking for a diameter, maybe you could just times this piece by 2 to find the diameter of a nucleus, and then times this piece by 2 to find the diameter of atomic radius. But because you're timesing both of them by 2 and then putting them in a fraction, those times by 2 on the top and the bottom are just going to cancel each other out. Long story short, it doesn't matter. You don't have to do it. So don't worry about that. I'm going to get going with this. Atom is 1.7 times 10 to the negative 10 over nucleus is 7.0 times 10 to the negative 15. So that's our ratio of an atom to a nucleus. we want to see what the ratio is in our real world drawing of our atom, which is unknown, so I'll call it X, to our nucleus, which we know is 1 millimeter. I'll just turn it into meters so we have common units here at 0.001 meters. To find X, we just need to multiply this over to the other side. You're going to find that X is actually equal to 24 meters. In other words, if you were to draw a scale model of an atom, where this right here, that little dot at 1 millimeter is your nucleus, then your electrons are 24 meters away. That would be a scaled drawing with a 1 millimeter nucleus. That's insane. That just shows you just how much of an atom is actually just empty space. Those electrons are buzzing around there, but they're not occupying all that much space whatsoever. Most of atoms are just completely empty space. Kind of crazy when you think about it that way, right? All right, anyway. Rutherford determined that the hydrogen nucleus had the lowest charge of any known nucleus and that the charge on the nuclei was a multiple of the hydrogen nucleus charge. The charge on a hydrogen nucleus is also equal in magnitude to an electron, so the hydrogen nucleus is known as a proton. That is true. A hydrogen nucleus is literally just a proton, right? It's a positive component that balances out the negative component of the one electron it has. So the nucleus of a hydrogen atom is just a proton. Rutherford's atomic model had the negatively charged electrons situated outside the positively charged nucleus. It was speculated that the electrons must be in orbit around the nucleus in order for them to not fall into the nucleus due to the attraction of their opposing charges. In other words, that's the whole reason they believe that they're spinning around. Them spinning around is what's keeping them from being attracted to it. And if you thought about this as a nucleus and this as your electrons, it's kind of like how, let's say, a rock would be attracted to Earth. But if it got caught in orbit, it's never actually going to hit Earth, because even though the acceleration is always pointing towards there, it's got enough, rotational centripetal momentum to it that it'll never actually strike it. And that's what they feel was the case with atoms. Moving on. All right, Bohr's atomic model. Rutherford, however, had recognized a critical flaw in his own planetary model of the atom. Accelerating charged particles emit EMR, electromagnetic radiation, and therefore lose energy. The electrons in orbit around a nucleus are constantly accelerating due to centripetal acceleration, and should therefore emit radiation, lose energy, and spiral into the nucleus, right? Since those electrons under Rutherford's model are moving in a circular motion, that would indicate that there is an acceleration, a centripetal acceleration, and from other experiments, accelerating charged particles emit EMR. That's what we're trying to say here. Now, another scientist who recognized this problem was Niels Bohr, who was also involved in extensive research dealing with atomic structure. Moving on. Now, what were the two main conclusions Bohr made about atomic structure? Well, the first one was electrons can orbit the nucleus only at certain distances. The distances are multiples of the radius of the smallest permitted orbit. Each orbit corresponds to a particular energy level. The total energy of an electron is quantized depending on its orbit. In plain English, what that first thing is saying is it's not a full-blown planetary model and they're not all spinning in all different directions. It's more that they appear in shells. So they'll appear at certain distances from that central nucleus. The further away you get, the more, okay, how about I put it this way? The further away you get, there's a change in energy, right? So each energy level has a different energy amount allotted to it. Those energy levels are directly related to the distance it is from the center. So in other words, the radius of its orbit. Next point, an electron can move from one energy level to another by either emitting or absorbing energy equal to the difference between the two energy levels, right? So in other words, an electron that's here in this energy level can actually go out to this energy level under certain circumstances, whether it emits or absorbs a certain amount of energy. Same with one out here. It can move out here and it can move all the way down to the center one if there is an exchange of energy of some sort, okay? We'll get into that in a second. So Bohr's model of the atom has electrons orbiting the nucleus in stationary states, a stable orbital level with fixed energy. The electrons do not radiate energy unless they jump from one orbit level to another. An electron must be in one of the specific orbital levels and cannot be located in between. They can, however, move between energy levels. So it's just repeating it again. An electron in each of these shells can move from one shell to another. Now, when electrons move between orbitals, their potential difference changes. Jumping up to an outer orbital means they gain potential energy. So the outer orbitals have more energy to them. So if you were an electron that was going from an inner orbital to an outer orbital, you'd be gaining potential energy. While if they fall to an inner orbital, so if they were on an outer one and then they fall down to an inner one, that would mean they've lost potential energy, right? So that energy has to go somewhere. It can't just vanish, because by conservation of energy, it has to go somewhere. So where on Earth does it go? Or where does it come from? You know, who knows? We're gonna have to find out here. Now, because energy cannot be created or lost, it must be conserved. When an electron jumps up to a higher orbital, it gains that energy from an incoming photon or from another source. So usually it's a photon, right? So in other words, a photon will come in and then provide that energy and move that electron to an outer level. That is, an electron absorbs a photon, which, remember, photons are just light energy, basically, when it jumps to a higher energy level. This is kind of like what we talked about before with Compton scattering. It's not exactly the same idea, but if you have a certain wavelength of light that comes in and strikes an electron, it's going to provide that electron some energy, which is going to allow it, as long as it's just the right amount of energy, to move to the next energy level, okay? Now, similarly, an electron will release a photon when it drops from a higher energy level. So in other words, if the electron was like, you know what, I want to go to an inner orbital level, it would actually have to lose energy, and the energy doesn't just vanish in thin air. It gets released as a photon, so it's some sort of light wave. Now, depending on how much energy gets released, that would indicate how much energy is in that photon, and therefore what kind of photon it is, because hopefully you remember E equals H times F. So in other words, the energy of a photon is that H constant times by the frequency of that photon. So if it released a lot of energy, you would have a very high energy photon. So maybe you have something like a gamma ray or an X-ray. It's possible, right? Now again, light of only certain wavelengths can be emitted or absorbed. It has to match that energy difference more or less, right? Moving on. Now the transition between energy levels follows the law of conservation of energy. The energy of the involved photon must be equivalent to the change in energy of the electron. So in other words, the energy of the photon is just equal to the difference between the final and the initial energy, and that again is of the electron for both of those, right? So another little picture here, let's say it was starting in an outer orbital, like the electron was out in an outer orbital, and then it dropped to a more inner orbital. Then there'd be a photon that would be released, of course, and that photon's energy is just the difference between the energy levels of those two energy levels there. Now that was probably a lot. We talked about a lot today. That was probably just a lot of like, whoo, whoa, way too much. Well, I got some good news for you, at least for today. We are now done. So for practice, I want you to work on Millikan's worksheet. It's just page 13 to 15. We're not going to do any practice today on Rutherford and Bohr stuff. By the time you guys watch this, I guess I would have recorded the next video. If you really care that much, if you're like, hey, whoa, that was cliffhanger. I don't want a cliffhanger. I want to figure out the rest of this. Then you can watch the next video and you finish off that lesson if you want all at once, but don't overload yourself here. I'm just giving you one bit at a time. So we'll finish learning about Rutherford and Bohr's models next class. We're gonna actually deal with that in a lot more detail, but we're gonna carry on with the things that we learned today. Anyway, I'm not gonna waste any more of your time. Definitely do those questions up at the top on Millikan's worksheet. It's not too many of them in there. And you know the drill. As always, please reach out to me if you have any questions.